Welcome to this video on gas clathrate hydrate thermodynamics, part of our module on subsea flow assurance and phase equilibria. It's prepared by Dr. Qureshi from National University of Singapore. He specializes in flow assurance and provides consultancy in complex flow assurance issues. In this first section, we will introduce clathrates, often referred to as the, quote, ice that burns. So what is a gas hydrate? They are ice-like solids where gas molecules are physically trapped inside a rigid lattice of water cages. Remarkably, they can form well above the freezing point of water if pressure is high enough. Hydrates form in three common crystal structures. Structure I typically involves small molecules like methane, while structure II is the most common in subsea operations, often forming with larger molecules like propane. The stability of the clathrate lattice depends on these guest molecules. Without them, the water structure would collapse into liquid at room temperatures. Essentially, the trapped gas stabilizes the crystal. Many substances act as guest molecules. Hydrocarbons like methane, ethane, and propane are key formers, along with non-hydrocarbons such as carbon dioxide. Conversely, molecules larger than pentane generally act as inhibitors. Remember that a hydrate plug is not just a simple blockage. It acts as a highly compressed gas reservoir within your pipeline, presenting a significant safety risk. The danger of expansion is severe. A single cubic meter of hydrate can release over 160 cubic meters of gas upon dissociation, enough to cause a pipeline rupture. Moving on to section 2, we will look at the thermodynamics and phase equilibria to map the boundaries of hydrate stability. The hydrate phase envelope defines the conditions under which hydrates are stable. Subsea tiebacks frequently operate within this stability zone due to the cold temperatures and high pressures found on the seabed. The van der Waals plateau theory provides the statistical foundation for predicting these equilibrium conditions, relating chemical potential to cage occupancy. Various parameters shift the equilibrium curve. For instance, increasing pressure moves the curve, while adding certain chemicals can inhibit formation by shifting the stability boundary. Gas composition is highly sensitive. Even minor amounts of propane or isobutane can shift a methane system, raising the dissociation temperature and increasing the risk of blockages. To understand the driving force for formation, we look at subcooling and overpressure. High subcooling, meaning a large difference from the equilibrium temperature, significantly increases the risk. In the final section of our video, we will discuss kinetics and crystal growth, distinguishing between whether hydrates can form and how quickly they actually do. Operating within the hydrate stability zone doesn't guarantee an immediate plug. Crystallization requires specific conditions, an oil-water interface, sufficient shear, and time. Plugs often arise during transient events like shut-ins or restarts. The hydrate formation curve reveals a three-step process: an initial, unpredictable induction period, a phase of rapid, exothermic catastrophic growth, and finally, a steady state. Induction time is highly stochastic. It is influenced by subcooling, where higher levels drastically reduce delay time, and by agitation or shear, which accelerate the process. The transformation from crystals to plugs occurs in three stages: nucleation at the fluid interface, agglomeration as crusted droplets stick together, and final bedding, where the slurry bridges the pipe, stopping flow. Locating a subsea plug is a major challenge. Operators use techniques like pressure pulsing reflectometry or deploying ROVs equipped with density scanners and thermal imaging to find the cold, dense hydrate mass. We now move to section IV, focusing on hydrate mitigation strategies and the use of chemical inhibitors. Chemical mitigation requires significant infrastructure, including topside pumping skids and subsea umbilicals. Chemicals are injected at the wellhead or downhole to treat fluids before they enter cold flow lines. The choice between thermodynamic inhibitors and low-dosage hydrate inhibitors depends on the specific operational requirements and cost-benefit analysis of the project. Thermodynamic inhibitors include methanol, which is highly effective but volatile, monoethylene glycol, which is recoverable and standard for gas fields, and salts that naturally reduce water activity. Methanol usage involves major logistical challenges. High concentration requirements for water-heavy production necessitate massive storage and specialized supply vessels, impacting project economics. Low-dosage hydrate inhibitors include kinetic inhibitors, which delay crystal growth using polymers, and anti-agglomerants, which keep hydrates as a pumpable slurry by preventing particles from sticking together. Finally, we conclude this video with an overview of advanced concepts and summary trends in the industry. When hydrates form in porous media, thermodynamics shift. Capillary pressure in rock pores can suppress formation temperatures, a crucial factor for drilling and energy resource evaluation. The industry is increasingly adopting LDHIs or hybrid strategies to avoid the high costs of heavy infrastructure, like heated pipe-in-pipe systems or large-scale chemical storage. This concludes Module 3 on gas clathrate hydrate thermodynamics. We look forward to exploring kinetics and additives in the next module. Thank you for watching this module. If you have questions regarding the topics covered or are interested in collaboration, please feel free to reach out via the contact information provided on the screen.